Hi everybody, thanks for joining us today and thanks for the panel that invited us to present our research. I'm really happy to be here today at the Cannes conference. I want to thank the panel again for choosing us as one of the 3 best papers. Today I'm going to show you a super cool attack. Actually it's a family of attacks and we call it cross-site search attacks. Using this attack we can leak plenty of private data from the victims. But before I'm having a deep dive into technical details, let me first thank again my partners and colleagues Nethanel Gelernter and Amir Herzberg. Amir will also present here later today a great workshop. I will be there also, so you are invited to join us. Let's start with the agenda for today. I will start with a short intro that talks about what we can leak using this attack. Then I'll present the taxonomy of the attack. As I said, it is a family of attacks, so I'll explain the model of the attack and the different types. In this presentation, I will focus on the length-based attack, and I'll show you a few attack vectors of this type. Then I'll introduce our reproducibility system, in which you can repeat our experiments, but also produce and test your attack vectors. I hope that after this presentation you will find out some attack vectors by yourself. I will also present the defense mechanisms that we suggest to use. Let me tell you some examples of sites that were vulnerable to our attack. See how many data we can leak using this attack. For example, we could leak structured content from your Gmail account, such as your credit card number. We could also leak private details from your Facebook account, such as page likes and hobbies. We can also leak your watch history on YouTube. The full list of the vulnerable sites is on our paper, so you are invited to see it over there. As you can see, our attack is based on 2 attacks, cross-site and side channel. In the cross-site attack, we assume 3 assumptions. The first is the victim is already authenticated to the service we attack. In this case, the service is Gmail. We assume also that the victim visits our malicious site. In this example, attacker.com. We also assume that the same origin policy is enforced and enabled, so one origin cannot access the data of another. It means that, in this example, our JavaScript that came from attacker.com cannot access the data of Gmail. This leads us to the side channel attack. We cannot directly access the data, but maybe we can leak the data piece by piece using a side channel attack. So let's see the figure on the right side of the slide. The victim visits our site. He gets back a malicious JavaScript. This JavaScript sends a pair of search requests. The first one is a real search request in the Gmail sent folder. It searches for all the emails that are sent from Vic. If the name of the victim is Vic, the response for this request will be a full response with many search records. The second request is a dummy request with a dummy generated name that will intentionally get an empty response. Our JavaScript will analyze those responses and using side channel analysis will know how many records there are in each response. In this example, we can know if the name of the victim is Vic or not. So, as I said, our attack is a combination of 2 attack types, cross-site and side channel. On one end, the attack is similar to the CSRF attack that leads us to a malicious link. And on the other end, it uses a side channel to leak data, such as many caching attacks that are very common these days. We have talked about side channels, but what are the side channels that we can use in our attack? So we will present today 2 types, a time-based and a length-based attack. We will focus on the length-based attack, but I'll make also a short brief of the time-based attack. Using the time and the length, we were able to find out how many search records there are in the response, and by that, leak private data. You can see that there are 3 time-based attacks. I will present today only 2, the network time and the cache time. And you of course can read in our paper about the processing time attack. So let's start with the network time side channel. As you can see in this attack, we measure the time it took the responses to get back from the server. We measure the round-trip delay and we repeat these measurements n times to get more accurate measurements. If the average round-trip delay of the real search responses is longer than the dummy responses, we can know that this is a full response with many search records. That way we can answer our query. The cache time attack is similar to the previous attack. We send a pair of requests, but this time we store them in a local cache. Then we will measure the loading time from the cache. We will repeat these measurements n times. If the average loading time of the real search response is longer than empty responses, we can know that it is a full response with many search records. So, time-based attacks are very difficult to implement. It is not an easy mission to make them practical attacks. There are many reasons for that. We have to exploit it in a short visit of the users, and we need to avoid detection by the servers. It is not trivial to do that because of the time measurements that are not accurate and depend on many factors in the servers and the clients. But, as I said, I will not focus on time-based attacks, but length-based attacks. It is time for a change. So, we are finally here. I hope that you stayed with me until now, because now the stuff is getting interesting. Now I present the length-based attack, and as you can see in this slide, the attack looks like the previous version of the attack. But now, instead of measuring the loading time and the delays of responses, we will expose the size of the response directly. We will do it using an exploit in some browser features. Before I'll show you how can we expose the exact size, let me tell you what we can do with the exact size. In this slide, we can see the structure of a typical search response. Each response consists of phi bytes of metadata and raw bytes of each search record. In this example, we have 4 search records. As I said, search records are the results of a search query. In the figure on the left, we can see how an attacker can use L, the response length, to calculate R, the amount of search records. He first finds phi and raw, the constant parameters of the response. The attacker can do it in advance for each service. Then, using L, the attacker can expose R, the amount of search records. So, now we know what we can do with L, the exact size of the search response, but how can we expose it? As I previously said, the same origin policy is enabled. We are not allowed to access the response data, so we will need to find an exploit to expose it. In the following slides, I will show you 3 attack vectors that let us expose the exact size of a cross-site response. The first one is an easy way in the Google Chrome browser to find the exact size of a cross-site response. First, you should know that developers can store responses in a local cache, and then using a function that's called query usage and quota, they can measure the usage of the cache. That way, using this simple function, we can expose the exact size of a response. We will empty the cache, store a cross-site response, and then measure the cache usage to find the exact size. As you can understand, it was an easy way to expose the exact size of a cross-site response, but then Google deployed a new Chrome version with a defense mechanism that denies this obvious way to expose the response size. The defense is a padding mechanism that should not allow an attacker to expose the response size. Google added a padding size, an unpredictable number of bytes, to the real size of the response. That way, an attacker that will use the query usage and quota function to measure the usage of the cache will not find the real size of the response, but a padded one. As you can see, we found out that the padding size was calculated using a hash function on the request URL, using a key that changed in every boot of the browser. The first thing we did is to think if we can statistically break this mechanism. Maybe we can measure the size many times and get some knowledge about the size. Chrome thought about that, and for this reason they did not change the padding in every single measurement. Responses originating from the same URL will get the same padding size. But who needs mathematics vulnerabilities when we have a logic flaw? So now we all know how this defense mechanism works, but how can we bypass it? So the key for success here is the fact that responses originating from the same URL will get the same padding size. We exploit this security feature and bypass the padding mechanism. That way we expose the exact response, and this exploit got a CVE from Google by their vulnerability reward program. So finally, some technical details as I promised. The exploit works as follows. We send two requests to the same URL and we get the same padding size for them. We send the first request without cookies, so no user is authenticated to the response, and the response will be empty. But the second request will be sent with cookies, so the victim is authenticated and the response is a real full response with many search records. It sounds complicated, but it is a simple trick. Let's see it in a figure. So, as you can see in the figure, the first request is sent without cookies, so the response is an empty one. The size of the response will be phi bytes of the metadata plus the calculated padding size. The second request is sent with cookies, so the response is a full response with some search records. The size of this response is phi bytes of the metadata plus the size of the search records plus the same padding size of the previous empty response. Now, using this simple formula, we can calculate R, the amount of the search records. The mitigation that Google proposed is to add the flag to the hash calculation. That flag marks if the response is sent with credentials or without. That way, the padding size will not be the same for these two responses. Note to mention that cross-origin read block, CORB, is another cool security feature that Chrome has introduced lately. It denies suspicious cross-site requests, so it may mitigate some of the attacks here. Another product that we used to perform our attack and expose the size of a cross-site response is Flash Player. Flash is currently supported in all browsers, and that makes our attack cross-browser. We used a specific feature that's called progress event. I will not describe the full technical details of that attack vector, but you are invited to see them in our paper and on our GitHub page. In the following slides, I will review how we optimized and enhanced our attack to expose complex data from the victim's accounts. We used 3 optimizations to make that. The first one is to perform efficient search algorithms. The second is to implement inflation techniques to increase the size of full responses. And the third one is the second order attack. I will not present the second order method today, but you can read about it in our paper. In this figure, you can see the taxonomy of the optimizations. We used two inflation methods. The first is to inflate the processing time by causing a delay in the server using specific queries. And the second one is to inflate the length of the response by increasing the size of the query. And we also have efficient search algorithms. The first is any term identification, ATI, that performs a search for an item from a closed list, for example a contact list. Another search method is a character by character search. It exposes the data character by character without any previous knowledge about the data. I will present in this presentation only the character by character search and its usage in our experiments. To perform a character by character search, the search engine of the attacked service needs to support partial word search. Then we can search for all available characters, one at a time. Once we found the first character, we can continue with the next character. The algorithm searches all available characters for each character in the string. OneDrive, for example, supports partial word search of the names of files and directories. So then, we performed a character by character search and exposed the list of all the files and directories of the victim. As you can see, the attack duration depends on the length of and the amount of the files. In this table, you can see the list of the top vulnerable websites and their Alexa rank. You can see also the supported features in their search engine, such as partial word search and other advanced features that make our attack efficient and effective. In the table you can see the most popular services, such as Gmail, YouTube, Facebook, and many others. As I said, we set up an infrastructure that you can all use to perform and test our and your cross-site search attacks. You should know that web services tend to get updates and change their API frequently. So, to ensure that you can reproduce our experiments, we create a VM and virtual machine with all the necessary services to test and perform cross-site search attacks. The system consists of the following services. We set up a local email service to simulate a real mailbox of users, and we use the Enron dataset. This dataset contains thousands of users and hundreds of thousands of emails. We configured a service that simulates real network conditions, including drops and delays. We also used a local web service that presents all the results of the search request. We set up a service that sends cross-site search requests to the local email service. We configured our three attacks: the network time, the cache time, and the length-based attack, to attack the email service. If you find out some attack vectors or think about another side channels, you can implement your attack there and compare it to our experiments. We have talked so long about the attacks and the vulnerable services. Now I'll present the defense mechanisms that can help to mitigate cross-site search attacks. On the client side, Chrome and other browsers should harden their Quota management API and make sure that the same origin policy is enforced in this API. Chrome also introduced a security feature that can identify and block suspicious cross-site requests before they reach the web page. But what web services can do to mitigate the risk if browsers are not fully protected? So, on the server side, we can use any of the well-known anti-CSRF methods, such as CAPTCHA or CSRF tokens. But web services should remember to enable these anti-CSRF mechanisms for all the APIs in their web server, specifically on the search APIs. Web services tend to enable it only for the APIs that performs actions that affect the server state, and that one poses a risk. So that's all for now. I hope you enjoyed it. Thank you very much.